Hello everyone, this is Mahsa Gorbani. I am going to present you the intelligent masking deep Q learning for context encoding in medical image analysis. This work is accepted for oral presentation of machine learning in medical imaging workshop of MICI 2022. This is a joint work between Technical University of Munich and Sharif University of Technology. In this work, we develop a novel self-supervised approach that occludes targeted regions to improve the pre-training procedure in the medical domain. We show that our novel masking strategy advances the learned features according to the performance on downstream disease diagnosis tasks. Deep supervised neural networks need a substantial amount of annotated data to demonstrate a state-of-the-art performance. Therefore, methods that do not require large data are becoming more and more interesting to train high-accuracy models with a fewer number of annotated samples. Self-supervision is a family of methods to pre-train deep neural networks using a large number of unlabeled data. Self-supervision strategies can be classified into two broad categories, including contrastive learning and pretext task learning methods. Contrastive learning methods are based on making the representation of similar images close to each other while making the representation of dissimilar ones further from each other. On the other hand, pretext task learning strategies extract auxiliary labels from unlabeled data and then solve a proxy task to learn semantic representation. There are context prediction, patch swapping, rotation methods, and so on. In this work, we focus to improve the in-painting strategy that is one of the main adopted approaches in recent years. In the in-painting strategy, which is first introduced by Patak et al. 2016, part of the unlabeled image is masked, and a convolutional neural network is supposed to predict the mask region. In order to succeed at this task, the network of the in-painting methods need to both understand the content of the entire image as well as produce an acceptable reconstruction for the missing part. They showed that adding adversarial loss to the standard pixel-wise reconstruction loss creates sharper outputs. However, they suggested that the pixel-wise L2 loss is sufficient for feature learning, although the output from the context reconstructor may be blurry. Similar but more customized self-supervised strategies are also explored in the domain of medical image analysis, from using follow-up MR images of the same patients to predict the order of the sliced images, or even funny tasks like recovering the 3D MR images as a Rubik's Cube. One of the most recent works from Chen et al. That we also compare our method against tries to swap random patches of the original image for a number of times and reconstruct the input. They train a convolutional autoencoder to reassort the original version in order to learn rich representation and meaningful image semantics. They showed that the network pre-trained through this method performed well in classification, localization, and segmentation tasks. In the existing methods, the transformations that are applied to build a self-supervision dataset are generally blind with random masking, rotation, or swapping. The in-painting is also similar, which we think is limiting its performance. In the current methods, all regions of the input image are masked with a uniform chance. This is a more serious problem when dealing with medical images where most regions may not contain relevant or any information, or when dealing with very large images like histopathological images. In this situation, we need much more targeted approaches. Besides, when training deep neural networks, the random masking strategy results in a lot of unnecessary network updates that cause the model to lose the rich extracted features due to network forgetting. We believe that choosing the appropriate transformations instead of random ones can improve both the efficiency and effectiveness of the training process. To this aim, we try to develop a masking model that learns an efficient masking strategy. However, for this purpose, there are two challenges. First, the main challenge behind finding an effective masking strategy is that choosing the mask area is a non-differentiable operation that cannot be easily optimized through an end-to-end gradient descent approach. Second, how should we decide what part of an image is a good choice to mask? What should be the criteria for this decision? To this end, we propose a reinforcement learning-based agent which learns to intelligently mask input images by taking discrete masking decisions and getting reward through many trials. On the other hand, we adopt an adversarial approach for training the masking agent in order to occlude the more challenging regions for the prediction model to regenerate. In the following, we first describe the prediction and then our proposed masking models and explain how we put them together. Given the input image X and a generated mask M hat by the masking network, our prediction model receives X tilde, that is a mask variant of input image. Then the prediction model is pre-trained to reconstruct the mask region using the context information in hand. To this aim, we use a deep convolutional neural network with an encoder-decoder architecture to capture the semantic of the input image. Inspired by context prediction method, which is introduced by Patek et al., we also apply a channel-wise convolutional layer right after the encoder to spread the information through the spatial dimension of the latent space. We use pixel-wise mean-squared error as the loss between the output of the prediction network and the original missing region. We develop a masking framework based on reinforcement learning to learn an efficient masking policy. To develop such an agent, we design a one-step episodic task in which the input image is the current state that creates a continuous, infinite state space. We also define the set of actions to be the set of overlapping image patches that can be selected to create a corresponding binary mask. And finally, we set the instant reward for our agent to be the loss of the prediction model. We employ Q-learning to train the agent by approximating a Q-value function with a convolutional neural network. Here is the final model, including a masking network along with a prediction network. In each episode, the agent receives the input image X, estimates the Q-values for all the masking actions, and then takes a sample based on the distribution of Q-values to mask an arbitrary region. After reconstruction, the masking agent receives the reconstruction loss as its instance reward, and then the episode terminates. During our training, since we sample the actions based on the distribution of the actions scores by applying a softmax function over the Q values, we have a balance between exploration and exploitation. Furthermore, to improve the stability of the training process, we adopt a two-phase training scheme where the masking agent operates completely random for the first few epochs. In order to evaluate the performance of our proposed self-supervised pre-training, we measure the performance of the pre-trained networks when being fine-tuned in downstream disease diagnosis tasks. We experiment on two datasets. In our first experiment, we model the presence of the abnormality in the brain MR images as a binary classification with the purpose of lower-grade glioma detection. The second dataset includes 2D ultrasound images collected from women between 25 and 75 years old for the breast cancer diagnosis. In our first experiment, we take 10% of the data for validation and 10% for testing in the pre-training phase. Thereafter, a class-balanced subset of the training set is selected to train the classifiers. We compare the performance of the classification task, especially when the training samples of the downstream tasks are limited. Intelligent masking outperforms the rest with a higher margin for lower sizes of training set. Other methods have similar performance in large training sets. However, they perform differently with limited number of samples. We take a similar approach for the second experiment. However, unlike the previous dataset, there are much fewer samples in each setup in this dataset. The results show that intelligent masking performs better, particularly with the smaller training annotations. We observe that context restoration shows lower results compared to context prediction. This might be due to the fact that our classification task needs the pre-trained network focus on the local structures like tumor regions rather than the global information. Here we present qualitative examples of different masking strategies. The first column from left are the original images of the two datasets, and the other column shows corresponding masking and swapping examples for pre-training. It is observed that, unlike context prediction and context restoration, our method tends to propose targeted masks like tumor regions or the ones with abnormalities. The code of the paper will be available soon. Please don't hesitate for any further question or collaboration to contact us. Thank you for your attention.